Good morning, students. Today we are going to study continuous charge distribution. But before that, let us just recollect what we have already studied. We have studied the formulas of calculating electric field due to a point charge at an even point around the point charge. Then we have also studied how to calculate electric field at a point due to a dipole and due to group of point charges. All these charge distributions are known as discrete charge distribution. Discrete charge distribution means all the charges are separate and far away from each other. But in actual practice, we need to calculate electric field due to charged bodies, and those charged bodies are known as continuous charge distribution. There are three types of charge distributions: linear charge distribution, surface charge distribution, and finally volume charge distribution. I will show you what a linear charge distribution is. Suppose if I have a long wire, not this one, long wire which is uniformly charged, then this can be considered as a linear charge distribution. Then suppose if I have a charged sheet like this, then it is known as surface charge distribution. And suppose if I have a charged body like this, then this can be considered as volume charge distribution. So in actual practice, we need to calculate electric field due to these kind of charged bodies at given point just around there. So first we'll start with linear charge distribution. Suppose I'm having a long uniformly charged wire. And I need to calculate electric field due to this uniformly charged wire at this point P. Now I don't have any formula to calculate the electric field at this point due to such a long uniformly charged wire. But yes, I have a formula to calculate electric field at this point due to a point charge. Now how can I consider this long uniformly charged wire as a point charge? So for that, what I do, I'll just divide this wire into small segments, very small segments, so that they can be considered similar to point charges. These small segments are known as line elements. Now, I'll calculate electric field due to this line element's charge at this point P. And as this line element is very small, I can consider it as a point charge, and so I'll write the formula of calculating electric field at the point P. Due to a point charge. We all know the formula, that is E is equals to K2 upon R square. This I have written in scalar form. If I want it in vector form, then I have to write a vector sign over here, and here I have to write a unit vector along the direction of the electric field. Okay. Now in this formula, I will be substituting values from the figure. So for that, instead of E, I will be writing delta E. Why delta E? Because this E is total electric field. And first we are going to calculate electric field at this point because of the charge of this small line element. So this won't give me total electric field. It will give me electric field because of this line element only. And that's why I will be calling this as delta E. This K will remain as it is. Q. This Q is total charge of the wire. But I am considering only this much length. So the charge on this length will be delta Q divided by this is the distance between the line element and the point charge, and this distance is suppose R dash. So instead of this R square, I will be writing R dash square, and as I have written here in vector form, I will be writing here a unit vector along the direction of electric field. Now what is this delta Q? To obtain the value of this delta Q, I need to know one quantity which is known as linear charge density. lambda, and its formula is delta Q divided by delta L. From this formula, we can write its definition. It is charge per unit layer. So this is the definition of linear charge density. Now, from this formula, I can calculate delta Q. See, from this formula, delta Q is equals to lambda into delta L. So I will be substituting this delta Q over here, and so I will get delta E is equals to this K as it is. Instead of delta Q, lambda into delta L upon this remains same. Okay. Now this is the electric field at point P due to this line element. But I want electric field at that point due to whole wire. So what I will be doing, I will be adding all the delta E due to all the small line elements in order to obtain total electric field. So the total electric field is equal to summation of all delta E. The constant quantities will come out. So K is constant and its value is 1 upon 4 pi epsilon naught summation of all delta L. This formula as it is. So this electric field is equals to lambda delta L upon R dash square into R dash cap. So this is the total electric field, because of this whole wire at point P. Okay, now suppose in exam they are asking you only linear charge density, then you need not write all these things. You will be writing till here. You will be writing the formula, you will be writing the definition, and then you will be writing the SI unit of linear charge density. So the SI unit of linear charge density will, see what is the unit of SI unit? Coulomb is the SI unit of charge and meter is the SI unit of length. So the SI unit of linear charge density will be Coulomb per meter. Okay. Now the second type of charge distribution was surface charge distribution, as we have discussed earlier. Suppose if I have a charge sheet like this, then it will be known as surface charge distribution. So what changes will make here? First of all, the figure. Instead of a linear wire now, we'll have a surface. Suppose if we are having a surface like this, and because of the surface, we need to calculate electric field at this point P. So again, as earlier, what we will do, we will divide this surface into small area elements. So suppose if I consider this area element, so now this is known as area element, and this will be a uniformly charged sheet, and we need to calculate electric field due to this area element now at this point P. So this will draw a distance of this point P from this area element, and suppose that is R dash. Now instead of linear charge distribution, we will be writing surface charge distribution. Instead of linear charge density, I will be writing surface charge density. And instead of the symbol lambda, we will be writing sigma. This is the symbol for surface charge density. So instead of the unit length, here we need to write this area element. That area element is delta S. So here we will write delta S. So that is charge per unit area. So now the charge in this area element will be from this equation. Delta Q is equals to sigma into delta S. And the SI unit will be coulomb. And what is the unit of area? That is meter square. So this will become coulomb per meter square. So if only surface charge density is asked, then you have to write till here. But suppose if they are asking you to calculate the electric field due to this surface charge distribution at point P, then again you have to do all this. So for that, till here the formula will remain same. Till here also same. Now instead of delta Q, we have to substitute sigma into delta S. So sigma into delta S. And this final equation, all delta S. This final equation will give you electric field at point P due to a charged plane sheet. So instead of wire, I will write a charged sheet. So now instead of this uniformly charged sheet, if I am having a solid body like this, then this will be known as volume charge distribution. So for that, we have to change the figure. Suppose we have a solid body like this. And we need to calculate electric field due to a solid body at this point P. So what we will do? We will divide whole this solid body into small volume elements, and then we will be calculating electric field due to that volume element at that point P. So suppose if this is volume element delta V. This is the volume element. So we will draw the distance of this volume element from point P, and that is suppose R dash. So this will become uniformly charged solid body. Instead of surface charge distribution, we will write volume charge distribution here, volume charge density, and the symbol of volume charge density is rho. Instead of delta S, we will be writing delta V, and it will become charge per unit volume. So now delta Q from this formula will become rho into delta V. Now the SI unit, coulomb, and what is the unit of volume? It will be meter cube. So instead of meter square, now we will write it meter cube. So if only volume charge distribution, volume charge density is asked, then you have to write it here only. And again, if they are asking you to calculate electric field, then you have to do all this procedure again. What you have to do is, instead of this delta Q, you have to substitute this value everywhere. So instead of rho delta, instead of sigma delta S, you will be substituting rho delta V. So everywhere here will change it. Instead of this, so this will be the electric field at point P due to a charged solid body. So that's all for the continuous charge distribution. We have studied linear charge distribution, surface charge distribution, and finally we have also studied volume charge distribution. So that's all for topic 1.13.